Hi, in this video we're going to learn how to prove statements by using counterexamples. In maths, generally the statements, the conjectures, they try to cover all numbers, but sometimes this is not possible and there are restrictions, limitations. A very simple example would be all prime numbers are odd. Well, thinking the prime numbers, right, it goes without saying that this is almost true. But remember, the first prime number is 2. This is our counterexample, right? So if someone says, well, all primes are odd, you just say, well, 2. So 2 is not an odd number, although it's prime. So this statement either must change or we can just consider this to be false, right? So we prove or disprove statements by using counterexamples. Let's see a proper example. The sum of two consecutive prime numbers is always even. Now this statement seems to be correct, considering all these prime numbers that we know, right? Like 3 plus 5 is 8, correct. 17 plus 19, this makes 36, correct. But remember that the first, say, the prime number is 2. If you add 2 and 3, you end up with 5, which is odd. And this is more than enough to disprove this statement. So what we actually will show is this. 2 plus 3 is 5 for 2 and 3 being consecutive primes. So since 5 is odd, the statement is not true. In this example, it gives us an inequality, right? And it says, find a counterexample to show that this inequality is not true when x and y are not both positive. Well, this is more like trial and error. So you can start, let x equals -1 and y equals 2. I just chose them arbitrarily. One is negative, the other is positive. That's what I want. Okay, so let's substitute now and see whether the sum is greater than or equal to 2. -1 over 2 plus 2 over -1. Well, this is equal to -1 over 2 minus, right, because of this minus sign, -2, because 2 over 1 is 2. So -1 over 2 minus 2, this is equal to, if you equate the denominators and take away, it's -5 over 2, well, which is obviously less than 2. So we can say shown that this statement is not true. Now let's look at this statement. It says, for every positive natural number n, 2n plus 1 squared plus 2 is prime. So basically, this is an odd number. So we're talking about an odd number squared plus 2. So if we add 2 to an odd number squared, right, the square of an odd number is odd, and if we add 2 to it, it's odd again. So basically we are talking about this odd number being prime or not. So we can just give it a try. So we can say for, let's say, n equals 2, right, this becomes 2 times 2 plus 1 squared plus 2, right? So 2 times 2 is 4 plus 1, 5. 5 squared is 21, 5. And 25 plus 2 is 27. Well, 27 is not prime, right? So we can say the statement is not true. So you can see that actually we are disproving statements. So this kind of does not make sense. Well, within our scope in P2, this is what we are supposed to do. But what happens is, actually that we use counterexample to prove statements by proof by contradiction. Now, this works as follows. Suppose you have a statement to prove. You just write the opposite statement and you disprove it with a counterexample. So, just because the opposite statement is false, the statement itself is true. Let's see an example. Now we know that there are infinitely many prime numbers, but we know this because it's proven. And you will see now how simple the proof is. Now let's consider the opposite of this statement, which is there isn't an infinitely many prime numbers set, but we have a finite number of primes. So let's write this down. Now if there are a finite number of primes, then we can list them, right? We can say P1, P2, P3, and so on as a list of our primes, right? And we can end up with a Pn for n being a natural number, right? So this is a finite number of primes. So finite means limited. So we can just write this as we have finite number of prime numbers. Now let's consider a number k written as P1 times P2 times P3. So it's the product of all primes, right? Plus 1. Now remember that any number which is not prime, which we call them as composite, can be written as product of prime numbers. Now consider 32, for example, right? You can write 32 as 2 to the power of 5, or you can write 36 as 2 squared times 3 squared, or you can write 72 as 2 cubed times 3 squared, and so on. Now, in these products, all these factors are prime. So this is prime product of prime numbers of these numbers. So what I'm saying is, if k is such a number, then there should be prime numbers which we can use in a product to get k. So we can write the product of prime numbers for k. Now, whichever prime you use to divide k, you will fail because of this plus 1. So if you try to divide k by P1, you're going to get the remainder to be 1. This will be true for any of the primes in this list. So just because k is not divisible by any of these primes, but we know that k should be able to be written as a product of prime numbers, then either there are prime numbers which is not in this list, so therefore our list is not finite, our list is not complete, or k itself is prime. So again, our list is not complete, and we can write such numbers like k, like there are infinitely many such numbers, right? So this concludes that just because our list of primes is not complete, so it's not finite because of this contradiction, then we say this statement is false, therefore the opposite of that statement is true. So there are infinitely many prime numbers. So basically this is how we use the counterexamples here. Our number k is the counterexample to show that there are infinitely many prime numbers, right? So we disprove the opposite statement to prove the actual statement. This is how we use counterexamples. But in our scope, within our scope, we will only disprove the statements, right? So they will be rather simpler than this. But I just wanted you to see how counterexamples work in maths. Thanks for watching.